Hi guys, afternoon. Just let me know if you all can hear me, please. Hi guys. So the paper you all got, it wasn't too bad. Saw the paper, right? So what I'm gonna run through in this session here, I'm gonna run through the solutions, right? So let's see. All right, so the first question said Statehook's law, right? So I did go through this in a crash course. What is Hooke's law? So basically, Statehook's law. So Hooke's law states that the extension is proportional to the applied force provided that the elastic limit is not exceeded. Right, so this is all I wanted here for that 3 marks, right? That's it. That's all I wanted here for that 3 marks. The next part, so that first part was a straight definition. The next part now, to determine the spring constant or the stiffness, so that's what spring constant is. It's the stiffness of a spring. A student placed different masses M on a hanger that is attached to a spring. So basically what they're telling us there is that we have a fixed support and we have a spring, right? And what we are doing here, so they said in this first part here, when you have nothing attached to the spring, the length of the spring is 70.2. So that's my length of my spring here, right? So this here is L0, or my original length, which is 70.2 centimeters, right? And then they start increasing masses. So then they're gonna say here what? We're gonna put some masses onto the spring and we're gonna measure the extension. That's essentially what they're doing here, right? So let's see what's happening here. So the first part here, they give us mass, but they give us mass in kilograms, and they wanted us to write this as force in newtons. So you all need to know that if you want to convert mass into weight, right, or force, we use this formula here. W is equal to m by g. Now they haven't given us what g is, but we will assume it's 10 based on this piece of information here. 0.1 kilograms, right? If we convert that into newtons, we multiply by 10. So all we're going to do here, we're going to assume that g is equal to 10, right? So for every single one of those readings here that they've given us, every single one of those masses, we need to convert that by multiplying by 10. So this here is going to be 2.0, right? Because you're taking 0.2 and multiply by 10. The next one here is going to be 3.0. This next one here is going to be 4.2. And this next one here is going to be 5.0, right? Now, this part here you need to be a little careful with. So they gave us, in this column we have length, but what we really want to work out is extension. So what we need to do, right? So we know the original length of the spring, it's 70.2. Now, to work out the extension, when you added this weight here, right, my new length is 74.4. So therefore, to get my extension, I need to subtract 70.2 from that, right? So let me use my calculator here rather than block this screen, right? So 74.4 minus 70.2, and you're going to get 4.2. So that's how they got this here, 4.2. So the next one now, if you want to work out the extension, we need to take 79.2. So you're taking 79.2, right? And we need to subtract my original length, which is 70.2, right? And what you're going to get here is 79.2 minus 70.2, and you're going to get 9.0 centimeters. So my extension here is 9.0 centimeters, right? I don't need to put the centimeters here, just 9.0. For this one here now, we're going to take 83.9. So this is 83.9, and we need to subtract the 70.2. So 83.9 minus 70.2, and you're going to get 13.7. So this here is 13.7, right? Let's just double check that next value there. 88.2 minus 70.2, right? So that's correct. So then to work out this last one here, we're going to take 92.7, and we're going to subtract our 70.2 again, right? So that's 92.7 minus 70.2, and you're going to get 22.5. So this here is 22.5. So what I've just done here, I've worked out the table, right? And all right, let's see what you're all saying here. Right, so this is it. This is it for 4 marks. That's all you need to do to follow this table, right? You need to convert your kilograms to newtons by multiplying by 10, and then we need to find the extension for each of those things there. Now, what else do they want us to work out here? They said using the grid, right? Using the grid provided, plot a graph of extension versus force. Now, when you're plotting these kinds of graphs, we need to know what kind of scale we're going to use, right? And you need to choose a scale that occupies most of the graph paper, right? You don't want a tiny scale. You want something that occupies most of the graph. So let's see, what did they say plot in the question? They said plot, right? So you're plotting a graph of extension versus force. So what that means, so don't confuse yourself, eh? It's extension versus force. So therefore it's extension on my vertical axis and it is force on this axis here, right? That's what I'm supposed to get. Extension against force, that's what I'm supposed to be plotting. Now, look at the values that we have. We have force going from 1 to 5, right? So your force, your smallest value here is 1 and your largest value is 5. So whatever scale we choose, it must cater for that. Then if we look at the extension now, you're going from 0 and your largest extension is this fella here, which is 22.5. So whatever you do, right, you need to make sure that we can fit 22.5 centimeters on your graph, right? So I've drawn in the axes for you guys here, right? So let's look how many marks you're getting for this. They're getting 8 marks for this. So there are certain things that CSEC is going to be looking for. They want to make sure that you label your axes. So you're obviously getting marks for this. Extension must be in centimeters, right? And you must label force in in newtons, right? And I chose a simple scale here on the horizontal axis, 2 centimeters for 1 unit. So on my horizontal, so my horizontal scale, right, I'm using 2 centimeters to represent 1.0 Newton. That's what I'm using on my horizontal axis. On my vertical axis now, right, because I want to cater, I want to reach as far as 20.2, right? Not 20.2, 22.5, sorry. That's what I'm trying to reach. So what I chose on the vertical axis here, so my vertical scale, right, in this scenario here, what I did, I chose 2 centimeters to represent 5.0 centimeters, right? That's what I chose for my scale here, right? Let's see now, what do we need to do? So now we need to plot the points. So the first point that we're going to plot, we're looking at the graph and make sure you're plotting the correct thing, right? They said you're plotting extension against force, right? So the first value we're going to plot is 0, 0. That's my first value. So you're looking at this column here and this column here in order to plot. So 0 against 0. So therefore my first value is going to be this. That's my first value here. The next value now is going to be, so this is my first point I plotted. The second point is 1.0 and 4.2. So 1.0, 4.2. Now you need to understand whatever scale you choose, you need to understand what the scale is. On my vertical axis, right? Every two of these small lines here, that's 1, that's 2, that's 3, and that's 4. You need to understand your scale. So I'm plotting 1.0 against 4.2. So let's see. 1.0 against 4.2, it could be around here, so, right? Now remember, when you're plotting your points, you should have used either a dot with a small circle around it or use an X, right? I'm not going to use either because I don't want to clutter the diagram. The next point I'm going to plot here is 2.0 against 9. 2.0 against 9. So 2.0 against 9 should be around here. That's 2.0 against 9. Then I'm going to plot 3.0 against 13.7. So 3.0 against 13.7. So this is 10, 11, 12, 13.5. 13.7 is around here, right? So around here. The next point I'm going to plot is 4.2 against 18. So 4.2 against 18. So this is 4.2 here, and we go in 18. So that's 16, 17. So that's about here, right? So that's 4.2 against 18. And the last point that I'm going to plot here is 5 against 22.5. So 5 against 22.5. Let's see where that is. So this is 20, 21, 22.5. 22.5 is here. So I've plotted it. Now remember, this is a Hooke's law question here. So therefore we know we should get a straight line, right? So let's see if, so what we're going to do now, we're going to draw a straight line that essentially passes through all of these points here, right? Right? So what you need to do, you're going to draw a line of best fit, right? And that's my line there. So in this question, for 8 marks, you're going to get marks for labeling your axes, choosing the correct scale, and all of those things, right? So that's that. That's the graph, right? That's what we need to plot. All right? So I it's the same graph here, right? Now the first part, they want us to find the gradient S of the graph, right? So you all should have known how to find gradient. So gradient, or my slope, is given by this formula here. y2 minus y1 over x2 minus x1, right? That's what I'm going to use. Now, you need to select 2 points on your graph, right, that you could use in order to do that, right? Now, let me use a different color here, and I'll select 2 points. Any 2 points. That's up to you, right? That is really up to you. In the exam, you could choose whatever you want. Let's get a different color here. All right, so I'm going to choose, and now I typically choose points that I have not plotted, right, unless the point is actually on the line. So I'm going to choose, let's say, this point here, right? And that point here, let's call it B for now, right? Let's call that point B for now. And I'm going to choose another point. I'm going to choose this point here, right? And I'm going to call that point A. So what I need to know the coordinates of A, and I also need to know the coordinates of B, right? In the case of B here, the coordinates of B here will be 4.5 against 20.0. So this A, sorry, not A, that's B. So I'm looking at B, right? B is 4.5 against 20.0, right? That's my B. My point A here is actually 0.5 against, and that'll be 2.5, right? This is 2.5. So you could select any 2 points you want and you will get the same gradient. It's up to you, right? Any 2 points you want, same gradient. So let's use those points here. So the point A is 0.5. So I'm going to just write it across here. So A is 0.5 against 2.5, 0.5 against 2.5. And the point B here is 4.5 against 20.0. So this is 4.5 against 20.0. But what I typically tell my students to do is to label these points. If you don't label it, you're going to run into problems. So I'm going to call this my x1, y1, because our coordinate is an xy value. And I'm going to call this x2, y2, right? So then all I'm going to do now, I'm going to substitute into this formula here. So this is 20.0 minus 2.5 divided by 4.5 minus 0.5, right? Now here's something that students have trouble with, and hopefully you all didn't make that mistake. So here's what I'm going to do. I'm going to work out the numerator first, right? I'm working out the numerator first. So that is 20 minus 2.5, right? And I'm going to get 17.5. So this here is 17.5 divided by, well, 4.5 minus 0.5 is going to give me 4.0, right? So this is going to be equal to, so I'm going to take 17.5 and I'm going to divide that by 4, right? And I'm going to get 4.375. 4.375, right? Now they didn't ask us for the unit, but if you look at the graph itself, so let me just move the calculator here. Right, so if you look at the graph itself, what you plotted, remember, this is what you plotted. This was force, and this was in newtons. This was extension, and this was in centimeters, right? Now, my unit in this particular case here is going to be centimeters Newton to the minus 1, right? So that's my unit here, right? That's my unit. So 4 marks for this, 4 marks for working out the gradient. Now some of you all may have gotten a slightly different gradient based on how you plotted the graph, right? No, the gradient doesn't have to be exact, right? It depends on what you drew, right? They're going to be looking at what you plotted. So your answer may be slightly different to what I have here, right? And somebody's asking, no, the graph is supposed to be a straight line. It's not a curve. This is Hooke's law we're dealing with here, right? And remember, everybody who will draw a line of best fit is going to be slightly different. It's going to vary slightly. So your answer for your gradient is going to vary slightly, right? All right, so now remember I drawing this on my laptop here, right? So my graph may be slightly different to what you got. So don't worry too much about that. There's a range of answers they will accept, right? The next part now, they said calculate the spring constant. So this is what they gave us here. They said S is equal to 1 over K, and they want us to find K. Now if I rearrange this formula, K is actually equal to 1 over my slope, or 1 over my gradient. So therefore, all I need to do is to take 1 divided by my answer I just got, 4.375. 4.375, and I'm going to get my spring constant here. So let's put this calculator back on here. And what I'm going to do, I'm going to say 1 divided by 4.375, right? And I'm going to get this as my spring constant. So 0.229. So 0.229. And in this case here, my unit, I'm going to write it as Newton cm to the minus 1, right? So we're getting 3 marks for working out the spring constant here. Right, so somebody's asking if it's wrong to use the plotted points. Now, the only time you can use the plotted points is if, when you draw your line of best fit, if those points actually lie on the line, right? Right, so 0.229, 0.23, right? Cool, so that's that. right? Let me move on quickly. The next part. Now they gave us a formula, right? Now typically they would tell you to find something from your graph, but what's happening in this part here, they said F is equal to K multiplied by E, right? And they want us to find the length, so they want the length when the force is of 8 Newton is applied. Now you gotta be careful with this here, right? So you want to get from this formula here, I can get my extension. My extension is equal to F divided by K, right? So for a force of 8 newtons, it's going to be 8.0 divided by my spring constant. So whatever answer you got, not necessarily what I have here, but what you got. So I got 0.229. So this is 0.229, right? So let's use the calculator to work that out. So that is 8 divided by 0.229. And you're going to get 34.9. So I'm getting around 34.9, right? So this here is 34.9 centimeters. Now, you gotta be careful. Look at what the question said. They said, what is the length, right? Now, remember, you know what the original length of the spring is. The length of the spring is 70.2. So this is not my final answer, you know. This is not the final answer. You have to do something else, right? So my original length of the spring, right? So my original length of the spring is 70.2, right? So it's 70.2. Now, what we just worked out here, we worked out extension, right? So when they say calculate the length, so therefore my length, so I know some people may not have done this. So the length is equal to, we have to take the original length of the spring, which is 70.2, and we need to add that to the 34.9. Right? I don't know how many of you all did that, but that's what we need to do. So what we're going to do here, we're going to say 70.2 plus my extension, which is 34.9, and I'm going to get 105.1, right? 105.1. So this here is 105.1 centimeters, right? Yeah, I figured a lot of you all may have missed that piece, right? All right, so that's it. That's 25 marks. You all got an easy 25 marks question, right? If you all had gone through the crash course videos that I did, right? Basically, I showed you how to work all of these questions, right? So that's question 1. Let's move on to question 2 now. So this one here, I heard some people got some trouble with this. So the first thing, define each of the following, the moment of a force. So the moment of a force, right, is the force. So it's the force, right, multiplied by the perpendicular distance from the pivot, right? Simple, straightforward definition. Now the way how the paper is, right, it's kind of hard to draw a sketch, but if you could have drawn something like this. Let's say that's your pivot, and this is your force here, right? That force has a perpendicular distance of, let's say, D from my my pivot, right? So this here is my pivot, or your fulcrum, right? So this is your pivot or your fulcrum. So your moment of a force, right, is simply equal to F multiplied by D, right? So it's 3 marks for this, right? Even if you didn't draw a diagram, that's okay once you put the correct words. The next part, part 2, they want to know what is my center of gravity. right? So the center of gravity is the point through which all the weight of a body appears to act. Right? As any simple definition like that, that's it. They just want a simple definition for center of gravity, right? Alright, somebody saying in the first question if they convert it to Newton meters, yeah, that's fine, they'll still give you the mark either way. Right, so that's it. 5 marks, definitions, right? Not much I can tell you here, right? And I think I also did this question in the crash course as well, right? State 2 conditions necessary for equilibrium. So when an object is in equilibrium, it means that it's not moving, right? So there are 2 conditions. One, the sum. So these are one condition has to do with moments. So the sum of the clockwise moments is equal to the sum of the anti-clockwise moments. Right, so that's my first condition. My second condition, right, is the resultant force acting on the body is 0. Right? This is not the first time they've asked this question. 2 conditions for equilibrium. These are my 2 conditions, right? That's what it is, right? Right? So the resultant force has to be 0, and that's it. So all of these are straightforward, right? I heard some people say this part they had some trouble with, right? Let's see. I didn't work this question as yet, so let me just read it through properly. So in the figure shown below, a diagram of a non-uniform. So look, this here, you need to pay attention to this word. Non-uniform means that my weight of this plank is not at the center of the plank. That's what that means, eh? So when you see the word non-uniform, that's what it really means. So we have a plank AB, and they told us, so let's see, the length of the plank is 2 meters long, right? Right, and the weight of the plank, so I'm just kind of highlighting what is important to us. So the weight of the plank is 1000 newtons. The plank is supported from the ceiling by 2 vertical springs, P and Q, and the plank is attached at a distance of 0.5 meters from each end, right? So those are the lengths that they gave us here. This is 0.5, this is 0.5, and we know the full length of the plank is 2 meters. And the center of gravity is here, it's at C. But because it's not uniform, it means that C is not at the center. So those of you who did that, right, in terms of how you work your question, that's not correct. Now here's what they want here. They said when a plank is horizontal, the tension in spring P is 600. So the tension, so let's have a diagram here, right? So the tension in spring P. So this is my spring P here, and this here is my tension. So this tension here, they said it is, how much? Oh wait, looking for it, it's wrong here, right. So they said it's 600. So my tension in spring P is 600 newtons. So this here is 600 newtons, right? Now at the same time, you're going to have a tension in this spring here, right? Let's call that T, tension in spring P, right? But we don't know what it is. We don't know what it is. Now the question is asking us, calculate the tension in this spring, right? Now, some people might think you have to do some kind of complicated thing for this, right? But you don't. Because this bar is horizontal here, all you need to do is say that your total upward force, right? Your total upward force is equal to my total downward force. So there's no complicated thing here to work out, right? And this has to do with resultant force. If the bar is horizontal, it means that my resultant force has to be equal to 0. So your sum of your upward forces must equal to the sum of the downward forces. So therefore, 600 plus my TP, the tension in spring P, is equal to 1000, right? Therefore, TP is simply equal to 1000, subtract, 600, and therefore my tension in spring P is equal to 400 newtons. That's it. 2 marks for that. Right? 2 marks for that. Somebody's asking if for the conditions, if you put upward force equal downward force, they may give you it correct. They may give you it correct. So that's 2 marks just for that, right? Let me move on to the next one here. Now by taking moments about A, determine the horizontal distance PC, right? Determine the horizontal distance PC. So let me get, hold on, let me get this diagram across here. Let's see if we can work this out here, right? I'm just going to make this a little smaller here, right? So here's what, we have the diagram, and they gave us a hint really here. They said taking moments about A. So we are taking moments about this point here. That's what we're taking moments about, right? We already worked out this tension here, right? So this here is 600 newtons, right? Now that's acting upwards, that force is acting upwards. The tension in this spring here is 400, and that's acting upwards as well, right? Now you're taking moments about about A. So therefore, this here is a clockwise moment. This force Q here is an anti-clockwise moment, and this force here is producing an anti-clockwise moment as well, right? So here's what we're going to do. We don't know, let's see, what do we know? You want to work out the horizontal distance PC, right? So this is what we're trying to work out here. You want to work out this distance here, PC, right? So we don't know what that is, but we're going to call that X, right? Because we don't know what it is. We know that the full length of this bar is 2 meters, right? We know that the full length is 2 meters. So therefore, let me use a different color here. So if this here is 0.5 and this here is 0.5, right? What I do know is that this distance here, right? 0.5 and 0.5 is 1. So therefore, we know that this here is 1.0 meters. That's what we know, right? Make sure we're doing this correct here because we need a kind of, right. So if we know that as 1.0 meters, it means that this distance here has to be 1.0 minus X, right? So I've labeled my distance PC as X, and I'm working from there now. So now, so I could see this question giving some people some trouble, right? So let's deal with let's say, clockwise moments. So my clockwise moments is equal to my anti-clockwise moment. Now it really is really sum. I just have enough space to write the word sum. So this is anti-clockwise moment here. Right, so let's see. The only clockwise moment we have is the 1000 Newton, right? So this is 1000 Newton. So it's 1000 multiplied by my distance from my pivot E, because we taking moments about the point E. So this here is going to be 0.5 plus X, right? So that's clockwise moments. That's the only clockwise moments I have. Everything else now is anti-clockwise. So in the case of the 600, it's going to be, so let's put this in brackets here. It's going to be 600 multiplied by 0.5, right? Plus, we have this one here as well. That's 400 multiplied by what's our distance there? 400 multiplied by, oh, well, you actually know that distance there, you know. So that's 400 multiplied by 1.5, right? So some of these things that I wrote down here, you don't really need it actually, right? As it is right now, we can work this out. So let's see. We're going to remove the brackets on the left-hand side. So 1000 by 0.5 is going to give me 500 plus 1000x, right? 600 by 0.5 is going to give me 300 plus 400 by 1.5. I know working the question for the first time, so if you all see a mistake, just let me know. So this here is going to be 500 plus 1000x is equal to 900. So 1000x is equal to 900 minus 500. So 1000x is equal to 400. So therefore x is equal to 400 over 1000, right? I think I saw somebody wrote this as the answer. So the answer should be 0.4, and that is 0.4 meters, right? 0.4 meters. Right, so I think I saw somebody say they got 0.4. 0.4 is the answer, right? So even though I wrote down the x and the 1.0 minus x, I didn't need that to work it out, right? I didn't need that at all, right? So this is my calculation here, and look at my marks I gave you for this, 5 marks. Right? So whatever you use to get the 0.4, that's fine. But the answer is 0.4, right? The answer is 0.4. All right, so let's see. What's the next part here now? State why the center of gravity is located closer to P than the point Q. That's an odd question. Why the center of gravity is located closer to P . All right, so the only way that I will probably answer this part of this question here, explain why. Now, I don't understand the intention, right? Sometimes they just need to get into the examiner's mind in terms of what they're looking for here, right? So if you want, they ask us why is the center of gravity closer to the point P than Q, right? Now, remember they told you that the bar AB is horizontal, right? So since the bar AB is horizontal, right? The weight, right? The weight, which is the 1000 newtons, right, must provide a clockwise moment to balance the total anti-clockwise moment, right? Now I'm just doing this based on the maths behind it, right? So since the bar is horizontal, the weight must provide a clockwise moment to balance the total anti-clockwise moment. This can only happen, so this can only happen if the center of gravity is closer to E. Right? Now I'm not sure what you all put for your answers, but this is how I would answer this, right? Yeah, that's what. So I seen somebody said the mass is concentrated closer to P, right? That seems like an obvious answer, right? And it's 1 mark for this thing here, right? So anything you say that makes sense, right? Chances are they'll give you the mark anyway, right? All right, so moving on, because I'm trying to cover the whole paper. So that is, oh, that's it. That's the whole of question 2. That's it. Now this next one here, question 3, the third question, explain what is meant by a transverse wave. So if you all did look at the crash course, I did cover this. So a transverse wave, if you have a wave moving in this direction, right, and the wave is made up of particles, right, it means that the particles are oscillating in this direction. That's what that means. That's what a transverse wave is. So explain what is meant by a transverse wave. The particles of the wave oscillate at right angles to the direction of travel of the wave. Right? So that's it. That's all they want here for 3 marks. That's what they want. And the next one here, we did this as well. Give an example of a transverse wave. Easiest one to remember is light. Right? Light is an example of a transverse wave, but you have other options as well. Right? You can say microwaves. Right? Infrared. Any one of those. Right? Anything from the electromagnetic spectrum, you'll get him out. Right? So, anyone. Next part, define the term ultrasound. So remember, the frequencies that we hear, now the normal human ear can hear between 20 and 20 kilohertz. Right? That's our normal range of hearing. Right? This is our normal range of hearing. So you all would have seen this. This comes in the multiple choice. Right? So it's 20 hertz to 20 kilohertz. Define what is meant by an ultrasound. So an ultrasound, and only 2 marks for this, right? A sound wave, so all you need to say, a sound wave with a frequency greater than 20 kilohertz. Right? That's it. That's all I want. Alright, let's see, somebody asked about a slinky spring. Well, if a slinky spring is moving back and forth, right, that's a longitudinal wave. But this question is asking us here for what is ultrasound, right? It's a sound wave and it has a frequency greater than 20 kilohertz. 2 marks for that. Give one example of an application of ultrasound, right? So we use it in medical imaging. right? So if you want to look at a fetus inside a woman who's pregnant, right? So we use it in medical imaging. We also use ultrasound to detect cracks in materials, right? So we use ultrasound for cracks in materials, right? Right. We also use it for measuring the depth of ocean. Any example that makes sense, you're getting marked, right? Any example, right? So I see somebody said prenatal scanning, yes. Sonar, yes. All of those things could work, right? So yes. So sonar, any valid example, 1 mark for that. Now, this particular one here now, so they have figure 3 shows the path of a light ray from air through a cube of ice. So we have air up here, right? So let us make sure we know this is air and this is ice here. What they want here now? Determine the angle of incidence on face MN. Let's go back to that diagram here. So, first thing, this is air and this here is ice, right? That's air and ice. This here, that dashed line here is my normal, right? So you have a ray that is entering from air into ice. And the question asks, what is the angle of incidence? So those of you who put 31 degrees, that is not correct, right? You need to measure between your normal and your incident ray. So therefore, this angle here is what they're asking us for. So that angle there is simply 90 minus 31. So angle of incidence here is simply going to be 90 degrees minus 31 degrees. And that's going to give me something. 90 minus 31, that's going to give me 59 degrees, right? So that's my answer, 2 marks. 2 marks for that, right? That's a giveaway. So that's that. Next thing they want, determine the angle of reflection on the face MN. So angle of reflection. Now look at the face they're talking about here. This is M, this is N, and it's being reflected. So here's what's happening here. Let me use a different color. So this here, we just worked this out. We got 59 degrees. Now, according to the laws of reflection, right, it means that this angle here also has to be 59 degrees. So that's not even my calculation. The answer is 59 degrees, right? And there's only 1 mark they gave for that. So that's what they want. So this here, my angle of reflection here is going to be 59 degrees. That's it. 1 mark for that. Next thing they want now. So what we knew that this angle here was 59. And they told us that the refractive index of ice is 1.31. Calculate the angle of refraction. So the angle of refraction they're talking about here is this. That's the angle that they want. Right? Now, so how I usually teach this in class, I use something like this, right? N1, so you all may have worked it out slightly different. So this is what CSEC says how we should teach it. And this is how I do it. So N1 sine theta 1 is equal to N2 sine theta 2. Don't worry if you never saw this formula, right? Some of you all may have worked it slightly differently. So you're going from air to glass. So the refractive index for air is taken as 1, and we're multiplying that by sine of 59 degrees, right, is equal to N2. N2 in this case is the refractive index in ice. So N1 for air is going to be taken as 1, and N2 for ice is going to be taken as 1.31, right? So like I said, don't worry if you didn't do it like this, that's fine, once you get the same answer. So this is 1.31 multiplied by my sine theta 2, which is what I want to work out. So this is sine theta 2. So therefore sine theta 2 is equal to, and that's going to be sine 59. Sine 59 over 1.31. So therefore sine theta 1. So here we're going to use the calculator now. Alright, so let's see what we're doing here. So sine 59. So we're going to press sine 59 on the calculator equal divided by 1.31. And you're going to get 0.65. Let's work that out, 0.654. So this here is 0.654. So therefore, theta 1 is equal to arc sine of 0.654. So therefore, theta 1 is equal to, and that's now, where am I? So let's pull back that calculator here, right? So all you need to do is to find second function sine, and you're going to get 40.9 degrees, right? 40.9 degrees. Right, so 40.9 degrees is my angle here, right? Let's move that calculator out of the way. Alright, so I see you all asking about the paper 3. Yeah, the students in my class, online classes, they're going to be getting some help, right? Alright, so 40.9 degrees, that's my angle here. So this angle here is 40.9. 40.9 degrees, right? Now, that's 4 marks for that. Now, on the diagram, label the critical angle for ice theta C, right? Now, I know what some students did for this particular question. I know what some of you all did. So some of you all went to the diagram, right? Some of you all went to the diagram and they said, so it's theta C, right? So some of you all went to the diagram and they did this. They say, yes, this is theta C. But that is wrong. That is not theta C, right? That is not theta C. So here's what's happening here. Now this ray here, right? This ray of light here, it is being totally internally reflected. Notice nothing came out here, nothing came out on the outside here, right? That ray got stuck inside of the ice, right? So what that means, so you see this angle here? This angle here is my angle of incidence, right, at that boundary. That's my angle of incidence here. Question wants, what is, or label the critical angle. Now, in order for total internal reflection to take place, what is supposed to happen is that my angle of incidence has to be greater than the critical angle, right? It has to be greater than the critical angle. So let's see how I can draw this without making this look messy, right? So let me erase this. So what you all have to do, right, you need to label your critical angle. So what I'm going to do, I'm going to just draw a line here. You could draw any line you want, right? Check this. Hold on. Let me just get a proper line. Yeah, I'm just going to get a proper line here for you all, right? Let's get a line here, right? So I'm going to draw a line here. Right, let's make it a little darker and probably a little thicker. Right, so that's what we have here. Let me just erase some of these things here as well. So I know many students would not have gotten this correct. So you see this angle here? This angle here has to be my critical angle for ice. So this here is my theta C, right? I hope that makes sense to you all, right? The key thing here is that you had total internal reflection taking place at NO, right? So if you had total internal reflection taking place, it means that the angle of incidence of your ray had to be greater than the critical angle for ice, right? So that's the answer, right? Like I said, I know some people, what would have happened, they would have left that out, right? Or they would have labeled the wrong thing, right? But don't worry, that's only one mark, small thing. Next part now. So that's question 3 we've taken care of. Question 4. On figure 4, sketch a graph of, so you're plotting pressure against temperature, right? So pressure against temperature, and that temperature is in degrees Celsius, right? And they want you to plot what's happening here. So if you plot in that, right, that graph is supposed to look like this, guys. That's what it's supposed to look like, right? It is not a straight line through the origin, right? And they give you 2 marks for this, right? That's the answer. Next part, explain how your graph could be used to derive the Kelvin scale. So, right, if you all, so this is what your graph look like, right? So this is pressure. This here is my temperature in degrees Celsius, right? Now, like I said, so the graph is supposed to be a straight line like this, right? Now, this particular graph is one of those graphs used to help establish the Kelvin scale. Now, if I extrapolate this graph here, right? If I extrapolate this graph, it is going to cut my temperature axis. So it's going to cut at minus 273 degrees Celsius, right? So explain how the graph could be used to derive the Kelvin scale. So you're going to say if the graph is extrapolated right, it will cut the temperature axis right at minus 273 degrees Celsius, right? This is used, so this is used as absolute zero on the Kelvin scale, right? So this is what we need to say in order to get that 2 marks here. So we extrapolate the graph, it cuts at minus 273. Yeah, I think you get marks for labeling. I see 2 marks here, you get a marks for labeling. Right? So I know some of you all may have done this. Some of you all may have done this. P against T, and they did this. That's wrong, right? Next part. They said using T to represent the Kelvin temperature and theta to represent the Celsius temperature, write the mathematical relationship. So when you have temperatures in degrees Celsius, right? If you have temperatures in degrees Celsius and you want to convert to Kelvin, all we do is add 273, right? That's all we do, add 273. So therefore the formula they want is this. T is equal to theta plus 273. Easy 2 marks here, right? Easy 2 marks. Next part here we have, what do we have here, right? So like I said, I know doing the paper, I really didn't look through the questions as yet. A container stores 5 meter cube of gas at a pressure of 13 atmospheres and a temperature of minus 273. Calculate the volume that the same gas would occupy at a temperature of 27. All right, so if we look at this question here, they've given us pressure, they've given us volume, and they've given us temperature. So therefore, my general gas law looks like this. P1 V1 over T1 is equal to P2 V2 over T2, right? Now, when it comes to the gas laws, there's something you need to pay attention to, and you gotta be careful. So my initial pressure, my P1, if we look at the question here, is 13 atmospheres, right? My initial volume, my V1, is 5.0 meter cube. My temperature, now this is where students will make mistakes. They gave you the temperature as minus 23 degrees Celsius. What you need to do, you need to make sure and convert this into Kelvin, please. So minus 23 plus 273, and that's going to give me, so let's work that out, minus 23 plus, right? And what I'm going to get here is 250 Kelvin. So this here is 250 Kelvin, right? When you're using the gas laws, it must work in Kelvin, not degrees Celsius. So my P2 is equal to, all right, so my P2 is 1 atmosphere. That's what it said there, right? My V2, right, you don't know what V2 is. That's what we're trying to figure out. You don't know what V2 is. And your T2, they said is 27 degrees Celsius. So this here is 27 degrees, but I need to convert that to Kelvin. So it's 27 plus 273, right? That should give me what, 300 Kelvin. Right, so that's 300 Kelvin. Now I can use the formula, right? So therefore, we're going to start off P1 V1 over T1 is equal to P2 V2 over T2. So my P1 is 13. So this is 13 multiplied by my initial volume of 5. Yeah, this is 5. Over my temperature, which is 250. Which is equal to my P2, which is 1 atmosphere, multiplied by V2, which I don't know. And then my T1 here, sorry, T2 is 300 Kelvin, right? So all you need to do here now is cross multiply. When you cross multiply this, you're going to end up with 300 multiplied by 13 multiplied by 5 all over 250, right? So this is going to give me 300 multiplied by 13 multiplied by 5 divided by 250, and what I'm going to get as my volume, I'm going to get 78 meter cube, right? I'm getting 78 meter cube. So like I said, I'm now doing the paper. I didn't do the paper before, right? So if you all see me make a mistake, just let me know, right? So I'm getting 78, right? Make sure you had to convert to Kelvin. If you all had looked at the crash course, I emphasize that over and over. You have to work in Kelvin when you're using the gas laws, right? And that's it. That's it for that part of the question. What else they have here in question 4? In question 4, they have 2 blocks, X and Y, identical except for the temperatures. So X is at a higher temperature than Y. Explain the difference in motion, right, of the particles in block X and block Y. Right, so we're talking about motion. So this question is about temperature. So what CXC is really trying to see is if you know that temperature, right, is dependent on the kinetic energy of my particles in that block, right? So the more kinetic energy something has, the higher the temperature. That's the basic idea here, right? The more kinetic energy something has, the greater the temperature. So if we're talking about the motion of the particles, so this is what we're going to say, yeah? So since block X is at a higher temperature, right? So since block X is at a higher temperature, right, than block Y, right, the kinetic energy of the particles in X is greater than the, I just write in shorthand here, right? Than the kinetic energy of the particles in Y. Than the kinetic energy of right? That's it. That's all I want here. We're talking about the kinetic energy of the particles. That's it. Yeah, I don't think they gave half marks, guys, right? So I don't think there's anything like half mark inside this here. Right? So 2 marks for this. The next part now. In which direction is thermal energy being transferred? So if the temperature of X is greater than the temperature of Y, right? What that means is that energy is going to travel this way. It's going to go from the higher temperature to the lower temperature. So in which direction is thermal energy being transferred? So all you need to say is from X to Y. That's it. From X to Y. Next part, state the condition under which the transfer of thermal energy ceases, right? So that part, what happens here is that when you have 2 objects and they are different temperatures and you bring these 2 objects in contact, right? What's going to happen is that energy is going to flow from one to the next. The one that is at a higher temperature to the one that is at a lower temperature. So energy is going to flow in that particular direction, right? Now, that is going to happen for a period of time until both temperatures of these 2 blocks are going to end up at the same temperature. When they end up at the same temperature, then there is 0 net flow of thermal energy between the 2 objects, right? So therefore, they said state the condition. So the condition is when they both reach the same temperature, right? That's the answer here, right? This is what we call thermal equilibrium. If you ever heard that word before, this is what you call thermal equilibrium, right? So in terms of wording of the question, the transfer of thermal energy does not cease, right? That's incorrect to say. Right? What is happening is that thermal energy is being transferred between both of them, back and forth. That's why you call it thermal equilibrium. So it doesn't cease, right? So that's a problem with how they wrote that, right? So that's 15 marks there again, right? That's question 4. Moving on, question 5. In figure 6, it shows a simple DC motor which consists of a coil of wire. All right, so I've never really seen them draw a diagram like this, but let's see. So you have a DC motor between the poles of a magnet. So you have south, you have north. The dotted line represents an axle about which the coil can turn. A current flows through the coil in the direction shown by the arrows. Okay, so based on the diagram itself, right, I'm going to make an assumption here. I'm going to assume that I'm looking at the diagram, I'm looking at the motor from on top, right, a top view, right? Based on how they've drawn the diagram, I'm going to assume that I'm looking at it from the top. So let's see, they said draw the magnetic field between the poles of the magnets, right? Between the poles of the magnet. I just wanted to get a copy of this fast here. I need to copy the diagram because I feel I might need it again, right? So on the diagram, they want me to draw the field. So you want the magnetic field. So you're drawing between a north and a south pole. What you're going to have lines looking like this, right? And I know some of you all may have put like curved lines here as well, and that's fine. You can put the curved ones if you want to, that's okay. But I'm just going to put the straight ones here. Now, what you're going to get the second mark for is for drawing the correct direction. So the direction of the field is this way. It's from north to south, right? So some people may have just drawn the lines, but they didn't put the direction. You need to put the direction to get the second mark, right? right? So for those of you who haven't, I want you to do something for me. Please hit like on my channel and please subscribe, right? And hit the bell, right? Just remember to do that before you log off from me, please, right? Now let's see what else they want here now. So that's 2 marks for that. Then they want state the direction in which the side dA of the coil moves as the current starts to flow. So we're looking at dA. Alright, I feel I need to put this diagram across here. Alright, so they want us to work out direction here, and then in the third part they said name the rule used to determine. Well, we can tell them the rule one time. It's Fleming's left-hand rule. Right? I just writing this here one time, but it's left-hand rule we're going to use. Now, some students have a lot of trouble with the left-hand rule. So here's what we're going to do. I'm going to use the left-hand rule here. Right? I don't know if you see my hands. It'll be kind of hard to do that. But your index finger gives you the direction of the field. Your thumb gives you the direction of the force. And your second finger gives you the direction of the current. Now let me look at this carefully and see. So you want dA. Right? So we're looking at dA. Let's see. So we're going this way. We're going this. Right. So remember, like I said, I am assuming, right, that the diagram they've drawn is a top view. So this is my assumption. So my assumption here. So this is my assumption. Right? What we're looking at is a top view. Right? That's my assumption. We're looking at it from the top. And if I use my Fleming's left-hand rule and I use north to south, this, it means that dA is going to move upwards. So dA, so this is steady direction. So dA is going to move upwards, right? That's assuming that I have a top view. That's my assumption, right? But you can also say that dA is going to move out of the plane of the paper, right? The exam paper we're talking about here, based on the left-hand rule that I just used there, that's what's going to happen, right? So we're using the left-hand rule, right? Yeah, so some of you all said upwards, right? That's the thing. I don't like how the diagram is, right? So if you say upwards, I would give you a mark. If you say coming out of the plane of the paper, that I will also give you the mark there, right? But I don't know what CSEC is going to do, right? So where am I now? Right, so 1 mark, 1 mark, that's it. Explain why a splittering commutator is used, right? So if you have a DC motor, right? If you have a DC motor, right? Yeah, so if you have a DC motor, right, and you didn't have the splittering commutator, what's going to happen is that that coil is going to start to move in one direction, and when it reaches horizontal, it's going to flip back, right? So when you don't have the splittering commutator, the coil is just going to move back and forth. It's not going to make a complete revolution. So the purpose of the splittering commutator is to ensure that the coil rotates in one direction only, right? So let's see. So the purpose, explain why the splittering commutator is used in a DC motor, right? And all you need to say here is to ensure that the coil continues to rotate in the same direction, right? That's the purpose of the splittering commutator, right? It's to ensure that the coil rotates in one direction only. If you didn't have that there, then it's going to just move back and forth, right? Next part, part B, right? Let's make sure, did we do everything? Third part, yeah, that was it. Honestly, I thought they were going to get something a little harder, right? Right, so we have an AC voltage here, right? And they said it's an AC generator, right? So it's an AC generator. And what they want here, calculate the value of the frequency. So they were nice to you guys, right? Because in order to calculate your frequency, so you need to first find what is the period. So your period is from this point here to this point here. So that's my period. Your period T for this oscillation is 0.02 seconds. That's my period. So what you're going to do here, you're going to say, so T is equal to 0.02 seconds, right? You got that from the graph. That's the first thing you need to do. Then you want to calculate the frequency. So your frequency formula is 1 over T. So this is 1 over 0.02. And you're going to use the calculator for that. That's what, 50? Yeah, you're going to get 50 hertz. Right? So that's my answer there. Right? Somebody's asking if I drew any magnetic field. I drew that already. That's it there. That's all they want. Right? So the video is being recorded, so you all can access it after if you want to. Right? Now, they said the peak voltage is applied across a 100 ohm resistor. Calculate the peak current. So basically, we have an AC voltage here, right? And you are connecting that across a resistor, right? That's what's happening. And the peak voltage here is, if we look at the diagram, my peak voltage here is 200 volts, right? So therefore, this here, so my VP, my peak voltage is 200 volts. The resistance here is 100, so R is equal to 100 ohms. And they want us to calculate the peak current. So remember, V is equal to IR. That's what we're going to use here. So my current I is equal to V over R. So my voltage, my peak voltage is 200. And you're dividing that by 100 ohms. And this is going to give me 2 amps. So my peak current is going to be 2 amps. Right, so the answer is 2 amps. That's what I'm getting here, and 3 marks for that. Easy 3 marks. The next part, the generator is subsequently rotated twice the frequency. State the effect it will have on the period and da da da. Okay, so this is an AC generator we're talking about here. This is not a DC motor. So this is an AC generator. So this is an AC generator, right? Now, you are rotating at twice the frequency, meaning that you're spinning twice as fast, right? Now, before I do anything, there's a formula here you need to remember. And that is your period is 1 over my frequency. Now, what we are doing here, we are doubling our frequency. If you double your frequency, right, according to this formula here, what's going to happen if you double your frequency? You're going to do this. You're going to have 2F at the bottom. You're doubling the frequency. So what that means is that you are going to half, right? You're going to half whatever your period was, right? So what is happening to the period? The period is going to be HALVED. It's going to be half. Right? So I know some of you all might say double. It's not double. It's going to be half. Right? Just now, in the question they gave us a period. So some of you all could have put down. So the original period is 0.02. Right? So what you could have said is that the new period is equal to 0.01 seconds, right? So the period is going to be halved, and you can put the figure if you want. It's up to you. I don't know how they're going to allocate the 2 marks here, right? But that's the answer there. And the second part, the value of the output voltage. What is going to happen to the output voltage? Now this is an AC generator. If you spin the coil faster, it means that your output voltage is going to increase. So all you're going to say here is that the value of the output voltage is going to increase, right? So the output voltage is going to increase, right? And that's it. That's the answer for question 5. Right, I see some of you all saying you leave the voltage the same. Now remember, remember how an AC generator works, right? A coil is cutting a magnetic field, right? Because it's cutting a magnetic field, it's getting an EMF induced in the conductor, right? The faster you move this conductor, the greater the magnitude of the EMF produced. So the output voltage is going to increase, right? So that's 15 marks again there, and we're on the last question already. So we have radium-226-88. It's represented by this 226-88 here. For a neutral, right, radium-226. So this is what we have. Let me write this a little bigger here. So radium-226-88, right? And you want the number of protons. So to figure out the number of protons, it's going to simply be whatever your atomic number is. So therefore, this here is going to be 88. That's it. There's no calculation there. The second part, the number of neutrons, we need to take our mass number, which is 226 minus 88, and that will give us the number of neutrons. So that is 226 minus 88, and you're going to get 138. So this here is 138. And the number of electrons. So they said it's a neutral atom, so therefore the number of electrons has to be the same thing. So most of you all should have been able to get that, this. So that's it, easy 3 marks. Let's move on to the next one. So radium-226 nucleus decays by emitting alpha emission to radon, right, nucleus. Explain what is meant by radioactivity, right? So radioactivity, right? Now you may not have the exact definition that I have here, right? Is a spontaneous and random process whereby an unstable nucleus attempts to become stable by emitting one or more of the following. Like I said, you may not have the exact definition that I have here, but anything along these lines, right? One or more of the following, right? And that is alpha particles, beta particles, or gamma rays, right? That's it. Anything along those lines. You may not have the exact same definition that I have here. All right. So anything along those lines, right? So basically, an unstable nucleus attempts to become stable by emitting alpha, beta, or gamma particles. That's it. That's what you want, right? All right, so I've seen some of you all have some definitions there. All right, cool. So next thing now, what do we have here? Complete equation for the decay. So we want to decay. Let's go back and see what they said. It decays by doing what? Right, so it decays by alpha particle emission, right? So it's radium-226 and you're going to radon, right? So therefore, if you're going to, let me just write this a little bigger. I don't like how this. So I have this 226 88. Right, and you're going to get Rn, right, and they said you're getting an alpha particle, right? So the alpha particle could be represented by this He42. So therefore, you need to make sure your mass numbers on the left hand side equal to the total mass numbers on the right side. So if this is 4 here, right, it means that this here has to be 2, 2, 2. If this is 2 here, right, it means that this here has to be 86. So that's it. That's all for 2 marks. Easy to marks. Next part, radium-226 has a half-life of 1600 years. Define the term half-life. Now, half-life has an easy definition, yet a lot of students, they end up write basically nonsense, right? So half-life, right, it is the average time. So half-life is the average time taken for the activity, right? Now you could use activity alone or number of atoms, right? So it's the time taken for the activity or the number of atoms to decrease by half its initial value, right? So that's what half-life is, the average time taken for the activity or the number of atoms to decrease by half its original value, right, or initial value. So 2 marks for that. What else do we have here, right? So at a certain time, a sample contains 8 by 10 to the power 8 radium nuclei. Calculate the number of alpha particles emitted by radium in the next 4,800 years. At a certain time, so let's see what they're really asking you for here. At a certain time, a sample contains 8 by 10 to the 8 atoms, right? Calculate the number of alpha particles. All right, just now, let's see. Okay, so they told us the half-life. Let me write down that here. So my half-life is equal to 1600 years. Right, that's my half-life for radium, right? So this is radium. At a certain time, so this is my initial amount of atoms. Calculate the number of alpha particles emitted by the radium nuclei in the next 4,800 years. So let's see. This 4,800 years, we need to figure out how many half-lives we have here. That's the first thing we need to do. So the number of half-lives, right, is going to be 4,800 divided by 1,600, right? So 4,800 divided by 1,600, and that is actually equal to 3 half-lives, right? So that's 3 half-lives. So what we're going to do, let's start off with this amount of radium nuclei, right? That's how much we have initially. After 1 half-life, so after 1 half-life, you're going to have half of that amount, which is 10 to the 8, right? Then we're going to go through a second half-life. So we're going to our next half-life here. You're going to divide that 4 by 10 to the 8 by 2. So you're going to get 2 by 10 to the 8, right? Then we're going through our next half-life again. So this is T1/2. And what we're going to end up with here is 1 by 10 to the 8. Now the question worded slightly different here. So let me see, what do they really want? Calculate the number of alpha particles emitted by the radium nuclei in the next 4,800 years, right? Now this here represents my initial amount, right? This is how much I have left, right? Therefore, the amount of particles that actually decayed. So this may have given some students some trouble, right? Let's see what you all said in the chat here. So number of particles that actually decayed, right? So those are the particles that converted from radium into radon, right? So number of particles that decayed, right, is going to be 8 by 10 to the 8 minus 1 by 10 to the 8, right? Because you started off with 8 by 10 to the 8 and now you have 1 by 10 to the 8. So therefore you're actually, this is how much actually decayed, right? This is how much actually decayed. So that's the number of number of radium nuclei that actually decayed. So therefore, remember, for each reaction, let's go back here. This is what's happening here. For every radon atom that decayed, you're producing 1 alpha particle, right? So if you know that this is the amount here, this 7 by 10 to the 8 nuclei decayed, it means therefore number of alpha particles emitted right, is going to be that same figure there, 7 by 10 to the 8. Yeah, so this question was a little tricky for some students, eh? So some of you all may have reached as far as the 1 by 10 to the 8. So yes, it can be, it could be a little tricky for some students, right? And then the last part, how much more time would elapse before the radium nuclei remaining falls to 0.5? So remember, you started off with 8 by 10 to the 8, right? Then after 1 half-life, so I'm just doing it like this again for you all. So this is 4 by 10 to the 8, right? And then our next half-life, you would have gone to 2 by 10 to the 8. Then we were at this point, right? 1 by 10 to the 8. That's the first part of the question. But now they said how much more time is going to be elapsed, right, when you get to this 0.5 by 10 to the 8. All you need to do, you're going through one more half-life. You're going through one more half-life to end up with 0.5 by 10 to the 8, right? So therefore, they said how much more time. So additional time elapsed, right, is simply going to be this. This is my additional time here. It's just 1 half-life, right? Is exactly equal to 1 half-life, which was, what was the original half-life? 1600 years, right? So the answer is just 1600 years. I see you all saying about the coil. Did I miss part of the question? With the coil, just now, hold on. For this question here, what did they ask? Oh yeah, I did miss out piece. Sorry, right? Oh no, the direction is just upwards. Direction is just upwards, or it moving out to the plane of the people. But like I said, the way how the diagram is drawn, my assumption is it's a top view of the motor, right? That's my assumption. It's a top view, right? So that side DA is going to move upwards or out to the plane of the paper, right? So if we were to look at it from a side rotated view, then it's going to be moving in a clockwise direction, right? But that's not what they asked us, though. They just want to know the direction of the side DA. Alright guys, so that's it there. I have completed all of the questions that you all got today, right? I've completed all of the questions that you guys did today. So all I want you guys to do is hit subscribe to my channel, hit a like, right? Don't hit dislike because you didn't get the answers that you wanted, right? I gave all the solutions in details, so please hit like, right? Hit like and subscribe, right? What else did I want to say? Right, so some of you all may be moving on to Form 6 eventually, right? And you may be using these books, right? I am the author of these two books, the official study guides for Cape Physics Unit 1 and Unit 2, right? I am the sole author of those two books. You might see some other names, but I am the author who wrote those two books, right? I just wanted to let you all know, if there are any Form 4 students here, my new Form 4 physics class is going to start in the first week in August, and this is intended for students who are entering Form 4, right? Alright guys, so the paper in general, it wasn't too bad, right? So that's it for me guys, right? So enjoy the rest of the evening, and hopefully I'll do a live sometime soon, alright?